In this video, we're going to look at the basics of electricity. Now, electricity is a topic that students often find hard, and this is true at GCSE, but it's also true in year 12 and 13. And to be honest, a lot of teachers don't really even fully understand what's going on because it is actually a complicated subject. So a good general principle when you're teaching anything in science is to start general, really embed the basic concepts and ideas, and only then get specific. And this is really, really important when we teach electricity. Start general, start with a theme, start with the ideas, start with models and analogies, and then get into the specific details. I might not always do it exactly that way around in this video, but when I'm teaching, I make sure to do it this way around. So in general, what is electricity? And students should have some idea of this from when they've looked at energy. It is a transfer of energy, and it's really important to make clear to students that in the way we talk about energy these days, electricity is a transfer of energy, and it's useful because then we can power devices and get useful work out of them. We can store energy in like a battery, for example. We could store chemical energy, and then we can transfer it as electricity. We're not storing electricity, but we are storing some other form of energy which we transfer into electricity. Or we can kind of make it as we need it, as in a generator. Now, a generator will produce a kind of push on the electrons in a circuit, and that is what we think of as electricity. But we can't store it. It either has to be used or it's wasted at the time. So this leads us nicely on to the idea of current, where current is the rate of flow of charge. Now, this is the best definition because it's not always electrons. It's usually electrons, but it could also be ions. For example, inside the body, if we're talking about nerves, if we're talking about like potentials across cells, for my limited understanding. Or it could be ions in electrolysis and chemistry. So it's nice to show this to students that it's not just electrons, but it usually is. So as a formula, we say that current is the rate of flow of charge. And it's really useful to use these words rate, which and also explain that it means per, or it means for every. So it's the flow of charge per unit time, or the flow of charge in 1 second. Right, and this understanding of what these words actually mean, divide by time, is really useful for students' understanding. So in terms of units, 1 amp is 1 coulomb per second. Now, a coulomb is a unit of charge. And this is a fundamental property. And it's fundamental in that it just exists. It's something that nature has decided is going to be there. A bit like kilograms, okay? We're all happy that kilogram is just a fundamental unit of mass. It's just there, right? We accept it. Charge, and therefore the unit of measurement of charge, coulombs, is also just a fundamental unit and quantity. And what else do we need to know about current? Well, obviously, we need to know that we need a complete circuit for charge to flow. It will only flow if there's a complete circuit. We need to know that positive to negative is what we call conventional current, and negative to positive is what the actual electrons are doing. And at this point, it's useful to talk about the history of this and why we have this, weird thing where there's two forms of current. And it's nice to tell a bit of a story at this point. It's nice to talk about the fact that electricity was being investigated before we knew what electrons were. When we discovered electrons, we decided they were negatively charged, but they just couldn't be bothered to rewrite the textbooks at this point. So they just ended up with these two conventions. And that usually provokes, some outrage of students, but it's good because it makes it memorable. If we're talking about a battery, of course, this is positive and this is negative. And a useful way of remembering, getting students to remember this, is to say, well, this long one you can chop up and make a positive sign, but this short one is just only short enough for a negative sign. The other useful thing to remember is it's technically a scalar, it's not a vector. Even though we can have positive and negative directions of current, it still is a scalar. There's something called current density, which is a vector, but it's not even A level, that's beyond A level. What else can we talk about when we talk about current? Well, we can talk nicely about the differences between insulators, conductors, and semiconductors. Now, this is not really GCSE, but it has a really nice link with chemistry. So we can talk about the periodic table. And if you think about the periodic table, what do we have? We have metals over here. These are good conductors because they have lots of free electrons, and we should be talking about the structure of metals with all these delocalized electrons at this point, and we should be linking what we know about chemistry and bonding and structure to electricity. And over here we have the non-metals, which do not have free electrons and typically insulators. And then we have this band here, which are semi-metals, which are sort of partial metals in their properties, but partially not metals. And these form semiconductors. So these are things like silicon, which obviously form the basis of all computers. So once you kind of point this out to students, a lot of things do start to click, at least if they are, average to high ability. And that is good because the more links you can make between different areas of science, the more their understanding progresses, especially in a difficult area like this. So this is current. The next thing we are going to talk about is potential difference, which is the formal or the scientific name for voltage. Voltage doesn't really mean much, even though we will use it all the time. I use it, but we should be talking about potential difference. And what is this? This is the push, or it's the energy to make the electrons move. So electrical current is when the electrons are moving, but why do they move? It's because they're being pushed by some energy, and that is the potential difference or the voltage. Formally, as a formula, potential difference is the work done per unit charge. So work done in joules per charge in coulombs. And this definition is really important, right, because it links this idea of energy moving charges, right, which is obviously the basics of electricity. The other fundamental quantity that comes up, maybe not fundamental, but the other really important concept that comes up is this idea of resistance, and this is, informally like the resistance to electrons flowing, right? But obviously we shouldn't really define things using the word we're trying to define, resistance to electrons flowing. So this is very much an informal definition. How we formally define it is the ratio of how much we need to push, or how much energy we need, to how much the current we actually get, how much flow there actually is. So obviously the formal terms we're going to use for this is potential difference, or voltage, divided by current. All right, so V over I equals R, and this is actually how we define resistance, even though this is the explanation, but the definition is this, and that's a really important but subtle distinction, especially when we get to A level. This is the definition, this is how we explain it. And what's really nice is you can then talk to students about what does it actually mean if we have a high resistance. Well, it means we need a massive amount of energy and we only get a tiny amount of electrons actually moving. If we have a low resistance, then we only need a tiny amount of energy and we actually get a large amount of charge flowing. All right, and this is actually really just kind of common sense when you phrase it in this term. So this is all very well and good. These are formal definitions, but how do we get students to really embed this and really understand it and visualize it? Of course, we're going to use some models. Now, broadly speaking, there's three types of models for electricity. There's the water model, where we're talking about some kind of water pump, and we've got some kind of circuit with pipes in, and maybe the pipes change size, maybe they flow uphill, maybe they flow downhill, and then we're making an analogy between the push of the pump, the flow of the water, and then how much flow we actually get at once. This is good, it works, there's a lot of good things about this, but at the same time, you sometimes end up having to explain a bit more about how water actually works. You sometimes actually just create some more issues with this. The other class of models is what we refer to as donation models. So there's multiple examples of these, and you can get students to create their own. The one I quite like is you've got a house, and in this house you've got a mother or a father, and the parent is giving money to children. And what do the children do when they get this money? Well, they get really excited and they run round the roads and they go and spend their money in the sweet shop. And then they come back empty-handed to their parents and they get some more money. And this is really good because one, it's memorable. Two, you can do a lot with this. You can talk about the money being the potential difference or the volts. That's what causes the children to run around in the first place. When they spend their money, that's obviously a transfer of energy, and that is when we get something useful happening. Right? And that's the whole point of electricity. It's only really useful, there's only a point to it when we transfer it, the same as any energy. We can then talk about the number of children being the current. So obviously once all the friends hear how generous this parent is, then all the friends are going to come round and you're going to get loads of children, and that is more of a current. And it also allows us to talk about series and parallel circuits, and if they're in parallel, the number of children splits, but the amount of money they have stays the same, which then gets us to talk about series and parallel. And it's quite easy for students generally to make this link between what happens in series and parallel with potential difference and current. However, for me, the most intuitive model is the rope model. And this is because it requires so little thinking from students that they just understand so many concepts very quickly. So what you need to do with this, you can actually do it physically if you have a rope, or you can just talk about it. And usually actually just talking about it is enough to get students to understand what you're on about. So you get everyone round in a circle, and then you get a rope, and the rope goes in a circle round everyone's hands. And then one person who's the teacher starts to push the rope round. That is obviously the potential difference, and therefore that potential difference creates current. And then students can see straight away that actually as soon as the teacher pushes it, as soon as the battery starts pushing it, there's current everywhere in the circle. One of the limitations with the donation model, which really does start to trip students up, is, how do the children over here know to come over here? Why don't all the children bunch up over here? Right? These questions are quite hard to explain, and students don't always understand that models and they have limitations built in, and that's almost the point. Maybe not the point, but that is the reality of them. So we know that a wire has electrons everywhere in it, but the electrons only start to move in a circle when you push them round. So this idea here is very nicely modelled in this. The other thing that we can talk about nicely here is what happens as it goes through someone's hands. There's friction. What does friction cause? It causes heating. And that is obviously a big part of electricity. That's what happens when you've got a bulb, when you've got any kind of component, when you've got a wire, the current causes heating. And then you can talk about what happens if this student starts to grip really tightly. Well, they're going to make the resistance go really high. What's going to happen when the resistance goes really high? Obviously, the rope is going to stop moving and you're going to get lots of heating. So you're getting these really, really complicated ideas where lots of things are changing all at once. And you're basically getting it for free because of this really intuitive understanding. So this is the best model, I think, for the vast majority of electricity. What it's harder at doing, and some of its limitations, series and parallel doesn't work quite as well. well, series works while parallel doesn't. You can make it work, but I think it loses its intuition. So I usually start with this model, and then when I get onto parallel circuits, I would probably switch to this kind of model. And then I would get students to try and explain this model here and start to talk about the limitations of the models. And that level of understanding is great for students. And if they can get to that idea where they can critique and compare two different models, you're doing pretty well. The last thing on this model, which I've sort of said, is what happens if the teacher pushes the rope faster. So if they increase their potential difference, well, again, of course, the current is going to increase, and you will probably also notice more friction, and you will notice, therefore, more heating. And again, this is a very complicated idea that you get intuitively. What else is important or useful? Animations like this one are very, very useful. So if you just type in Google, you can get to this fairly quickly. This nicely shows you the kind of inside of a wire, and it shows you that there's electrons there all the time, but they only start to move once you create a full circuit, a complete circuit, and once there's a potential difference across it from the battery. So this nicely encapsulates kind of the rope model, and it's probably something to bring in after you've talked about the rope model. The other thing that comes into basics of electricity is drawing circuits. Now, students often find this hard, especially in year 8. And one very, very useful way to introduce this is to constantly flick between photos of equipment and a couple of different types of equipment, and then your actual circuit diagram. And then when we come to draw actual circuits, we can take this one step further. We can have our photo of our equipment. We can have a kind of drawing of it, as students might instinctively do, and then our actual circuit diagram. And having these layers where we have photo, drawing, circuit, formal circuit diagram is really, really important because they can then instinctively match up the different components. They will then start to see, oh, this is a battery, this is a battery. The wires are really messy here, but actually it makes sense to draw them here and draw them neatly. So this approach is encouraged. There's also a couple of really, really good simulations, and I will link to these in the comments. Falstead.com/circuit is really good. You can build your own circuits and you can model them. It's best for A level, if I'm being completely honest. The PhET simulation is really good. For basics, it's a bit more visual, it's a bit more simple, and there's loads of information here, spark.op.org, where they talk about electricity and how to teach it. And I will also link to a really good website for drawing circuit diagrams quickly and easily, because often that can be quite time consuming.